Okay, going to start working on 8.7. I'm going to look at number 5. So this is the section Taylor and Maclaurin series. So number 5, they give you a function f of x equals 1 minus x to the negative 2. And they want you to find the Maclaurin series and also find the radius of convergence. And we're going to assume that there is a Maclaurin series for this. That's what it says. So, well, what is a Maclaurin series? Maclaurin series is a Taylor series about a equals 0. That's what a Maclaurin is. So what we need to do is we need to rewrite this using the fact that our function should be able to be rewritten as a sum n equals 0 to infinity c sub n x minus a to the n. And here a is 0. So all Maclaurin series look like this. So I need to find the Maclaurin series. So the question is, how do we get these c sub n's? And that's what this section is about. Remember that your c sub n's are equal to the nth derivative of the function at a over n factorial. And here a is 0 because it's a Maclaurin series, so we can replace that a with 0. So what I need to do is I need to take a look at this function. I need to start taking derivatives of it. And as I take derivatives, compute this value, and that should give me what these c sub n's are. And then I can start writing out the Maclaurin series. So let's try and get these c sub n's. So first of all, let's take a look at some of the derivatives. The 0th derivative of the function at x means you don't take the derivative at all. So it's just 1 minus x to the negative 2. Now next to this, I'm going to write down what is the 0th derivative at 0. And you know what, let's just do this. So we've got this equals, plug 0 in here. When you plug 0 in here, you get 1 raised to negative 2. That's just 1. So that's no big deal, just 1. And then we take the first derivative. So now we just bring out the negative 2. 1 minus x. We subtract negative 2, take away 1, we get negative 3. And now what we'll do is we'll figure out what the 0th derivative, or sorry, the first derivative is at 0, because it's a Maclaurin series again. Plug in 0, we get 1 to the negative 3, that's still 1, but then times negative 2, so negative 2. You know what, I forgot chain rule, hold up. Chain rule, derivative of this, negative 2 comes down, derivative of the inside is negative 1. I'm trying to rush through this. So when we try and plug in 0, we get the negative and negative become positive, so that's 2. Now I take the second derivative at x, and now watch what happens. This negative 3 comes out and hits, but remember this together is a 2. So when these two hit each other, I have a 2 here really, and that's going to multiply, it's going to be negative 6, but watch the way I write it. I'm going to say 2 times negative 3, and then I have the 1 minus x to the negative 4. So that's this coming out, hitting the 2 that was already there. And then I have the derivative of the inside, which again is negative 1. So on this one, I think I'll clean it up. This is going to be a positive 2 times 3, 1 minus x to the negative 4. And now if I try and take the second derivative at 0, I plug in 0, I get 1 here, and I get 2 times 3 is 6. But I'm just going to put 2 times 3. You'll see why. And then we take the third derivative. Okay, the third derivative at x So now bring this negative 4 out here, and it'll be 2 times 3 times negative 4, then 1 minus x to the negative 5, but then chain rule, derivative inside is negative 1. So this is just going to be 2 times 3 times 4, 1 minus x to the negative 5. And now if I plug in 0 into that, again, this is going to be 1, and we just get 2 times 3 times 4. And if we continue this, we'll see a pattern here. That if we want to know what's happening at the nth derivative, right? At 0, so I'm trying to figure out a pattern over here. Notice that the 0th derivative we have 1, the first derivative we have 2, the second we have 2 times 3, the third we have 2 times 3 times 4. So the pattern is that whatever this number is, this right here is always that number plus 1 factorial. So this, if we take 2, add 1, we get 3. This is 3 factorial. It's really 3 times 2 times 1. If we take 1, we add 1, we get 2. 2 factorial is 2 times 1. If we take 1 and add it to that, we get 1, and 1 factorial is 1. This one right here, if we add 1 to 3, we get 4. 4 factorial is 4 times 3 times 2 times 1. So this is correct. We see the pattern, hopefully. So what this will be is n plus 1 factorial. So now let's go back and look at what we were supposed to see here. The function should be able to be rewritten as a sum n equals 0 to infinity c sub n times x to the n, where c sub n was the nth derivative at a, which is 0, over n factorial. So I know that these look like this, but we just showed that this is n plus 1 factorial, and then over n factorial, which means that if we peel off on top n plus 1 n factorial over n factorial, they cancel, and so you just get n plus 1. And so my function, this function should be able to be written as sum n equals 0 to infinity of n plus 1 times x to the n. And that would be the Maclaurin series for that function. Now, finding the radius of convergence means that you would run a ratio test on this, which I'm not going to do, all right? But I'll just let you know that when you do the ratio test on this, you get absolute value of x less than 1. So your radius of convergence is 1. All right, so that was the first example. Let's see if we can do another one and start picking up on the pattern here. All right, the next one is e to the negative 2x. F of x equals e to the negative 2x. And so again, we should be able to rewrite this as sum n equals 0 to infinity c sub n x to the n, because it's a Maclaurin series. We have just x to the n, not x minus a. Well, we do, but a is 0. And our c sub n's will be equal to the nth derivative of the function at 0 over n factorial. All right, so let me start getting a handle on these derivatives. The 0th derivative of this function is going to just be the function itself, e to the negative 2x. If I take the 0th derivative and I plug in 0, because this is a Maclaurin series, then I plug in 0 here, e to the 0 is 1. All right, now let's take the first derivative. The first derivative of this function, I have a little bit of chain rule to do here. Derivative of e to the negative 2x is itself, but then times negative 2, the derivative of the top. So negative 2 e to the negative 2x. If I now take that derivative, plug 0 in, This is going to be 1, and I just get negative 2. Now if I take the second derivative, I cover this up, the derivative of e to the negative 2x is again negative 2 e to the negative 2x, but I had a negative 2 out here, so this is going to become a positive 4 e to the negative 2x. And if I plug in to the second derivative 0, I just get 4. So what's going to happen next time? When I do my third derivative, I get another 2 that's going to come out, another negative 2 is going to come out when I do this. If I cover this up, I get another negative 2 coming out. So that's going to turn this into a negative 8 e to the negative 2x. And then if I take that third derivative and I plug in 0, I just get negative 8. And let me just do one more. If I do the fourth derivative at x, am I recording? Yes. That'd suck. Fourth derivative, I get another negative 2 that comes out, so that'll be 16 e to the negative 2x. If I plug into the fourth derivative 0, I get positive 16. So what I'm looking for is a pattern in these, and I think I see it. These are all powers of 2. This is 2 to the fourth. This is 2 to the third. This is 2 squared. This is 2 to the first. This is 2 to the 0. But it's switching signs also. And so it looks like this 0 matches up with this power. This 1 is this power. This 2 is this power. So what I want to do is try and make this thing alternate, starting with positive, then negative, positive, negative, and remembering that my end's going to start at 0. So how can I make that happen? How about if instead of 2, I put negative 1, right? This was negative 1 to the 0, 2 to the 0. That's this one. This one is negative 1, sorry, this one right here is negative 1 to the 1, 2 to the 1. And then this one right here is negative 1, but this time squared, then 2 squared. And then this one right here is negative 1 cubed, 2 cubed. And then this one right here is negative 1 to the fourth, 2 to the fourth. So all of these are just what? Negative 2 to the 0. This one is negative 2 to the 1. This is negative 2 to the 2. Negative 2 to the 3. You may have seen that without me going through all that detail right there. So that's my pattern. So what then can I say about this? What's the nth derivative at 0 going to be? Well, remember that this derivative tells us the power on the 2, on the negative 2. That's all it does. So my c sub n's in this formula, or in this particular function, should be negative 2 to the n. And then it's always divided by n factorial. So we have the original function, this one right here, can be written as the power series starting at n equals 0 to infinity of this negative 2 to the n over n factorial times x to the n. That is the Maclaurin series for e to the negative 2x. And you could find the radius of convergence by doing ratio test. And what you'll find on this one is that the radius of convergence is infinity. So it turns out to be one of those ones where when you run the ratio test and you do the limit as n goes to infinity, that one piece goes to 0, and so x doesn't matter anymore. I got some good markers. Digging through my desk, I found some markers from like several years ago, and they're still good. All right, f of x equals sine of pi x. Okay, this is going to be interesting. All right, so we should be able to rewrite this. Let's just start taking a look at the derivatives. So the 0th derivative of this function is just the function itself. And if I plug 0 into this, sine of 0 is 0. All right. Now the first derivative. First derivative of this, well, derivative of sine of something is cosine of it, but then the derivative of the inside here would be pi. So I'm going to get pi cosine of pi x. And now when I do the first derivative at 0, cosine of 0 is 1, but then times pi, so I have pi. Now when I take the second derivative, what's going to happen is I'm going to get, pi is going to be here, derivative of cosine of something is negative sine, but then derivative inside is a pi. So I'm going to get negative pi, that's the derivative of cosine is negative sine, the pi that was here, it's going to be sine of pi x, but then times the derivative of what was in here, which is another pi that I can put out here, or I can just square that. And now when I take the second derivative and I plug 0 in, it's not going to matter because sine of 0 is 0, so this is 0. Now we do the third derivative. And what we do is we keep doing this until we find enough of a pattern. So when I take derivative of sine of something, it's going to be cosine of it. And then the derivative inside, I'm going to have a pi. That pi is going to come out and join this one. So I'm going to have a negative pi cubed cosine of pi x. And when I take this third derivative and I plug 0 in, this time cosine of 0 is 1, I get negative pi cubed. All right, so next one. Fourth derivative. Okay, this time take derivative cosine and get negative sine. The negative is going to come out right here and make that a positive. So positive pi sine of pi x. Derivative of the inside is another pi, and I had pi cubed out there, so pi to the fourth. And it won't matter because when I take the fourth derivative and I plug 0 in, it's going to kill everything off. I get 0. One more. Fifth derivative. Okay, so fifth derivative of sine is cosine. The pi is going to pop out, so pi to the fifth, cosine of pi x. And then when I plug in 0 into this, I just get positive pi to the fifth. Now it's a little harder to get a pattern on this one directly, because what you see is that when we plug in 0, we get 0. When we plug in 1, we get pi. 2, we get 0. 3, negative pi cubed. 4, we get 0. So at every even number, we're getting 0. At every odd number, we're getting something to do with pi. And it looks like it's alternating also. So notice here, right, I'm circling all the odds. Okay. Hold on, let me take this call real quick. This one's a little bit harder to pick up, like I said, because what's happening is we do have a pattern, but it's only occurring at odd derivatives. So the best way that the way that I like to approach this is I like to write out what this series is supposed to look like. Okay, so we know that this is supposed to be the sum n equals 0 to infinity, right, of c sub n and then x to the n. And I can tell, well, you know what, this should be c sub 0 x to the 0 plus c sub 1 x to the 1 plus c sub 2 x to the 2 plus c sub 3 x to the third plus dot dot dot. Now, remembering the fact that c sub n is the nth derivative at 0 over n factorial, that means c sub 0 would be the 0th derivative at 0, which is this, which is 0 over 0 factorial, which is 0 over 1, which is just 0. So my first term here is going to be 0 times x to the 0. That's just 0. Plus, now c sub 1 is going to be the first derivative at 0, which is pi, over 1 factorial, which is just pi. And it's positive, right? So pi. And then that's pi, and then x to the first power. Then when I do c sub 2, right, it's going to be the second derivative. That's going to be 0, so I'm not going to have anything. Plus, now when I do c sub 3, watch what happens. C sub 3 is the third derivative at 0, which is negative pi cubed over 3 factorial. So this should actually be, I'm going to change this plus to a minus, minus pi cubed over 3 factorial x to the third power. So that's this one. And now I need to keep going to try and really get this thing under control. The fourth one is going to be 0 because we knew that from all the evens being 0. The fifth one is going to be c sub 5 is going to be the fifth derivative at 0, which is this, pi to the fifth over 5 factorial. So that's going to be pi to the fifth over 5 factorial, and then x to the fifth. And what do we think the next one's going to be? For 6, it should be 0. And then we're at the 7th one, right? So we should have, it's going to alternate. We're going 0 and then positive, 0, negative, 0, positive, 0, negative. So I should have negative pi to the 7th over 7 factorial x to the 7th plus dot, dot, dot. And that keeps going. So let me now rewrite this. Get rid of all those zeros. Pi x minus pi cubed over 3 factorial x cubed plus pi to the 5th over 5 factorial x to the 5th minus pi to the 7th over 7 factorial x to the 7th plus dot, 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 dot. And what I'm going to do now is I'm going to just use my ability to rewrite the sum using sigma notation. And I'll start it out at n is 0 to infinity. And I want to create an alternating series. And I want to start with positive. So to do that, I'm going to go negative 1 to the n. I want to start at positive 1, or positive. So negative 1 to the n, if I start with 0, I get a positive 1, and then if I go with n is 1, it will be negative, then positive, then negative. So this should create the alternating part. Then I have here, all these powers on the pi's are all odd numbers. So I need to do pi raised to odd numbers starting at 1. So 2n minus 1. If I plug in, plus 1. If I plug in n is 0, I get 1. n is 1, I get 3, n is 2, I get 5. I want to divide that by all of these are odd factorials, including underneath this pi there's a 1 factorial. So these are all odd factorials starting at 1. So again, 2n plus 1, but then factorial. And then all of the powers on the x's are odd. So I have x to the 2n plus 1 again. And that should do it. That should be my power series right there. What number was this? Good. And maybe I have time for one more. Yeah, let's try and do one more. This one's going to be nasty. Number 8. So that problem was an example of one where you have to write out the terms in order to pick up the pattern and to be able to rewrite it easily. So I'm looking at the function x cosine x. And I'm trying to write the Maclaurin series out for this. And so I need to start getting derivatives again. So the 0th derivative of this function is itself. And then the 0th derivative at 0, thank goodness, because it's a Maclaurin series, is going to be 0. Now the first derivative, I'm going to move over here a little bit, the first derivative of this function requires a product rule. So the derivative of the first one is 1 times the second, plus derivative of the second one, which is negative sine x, times the first one, so negative x sine x. Now, if I take that first derivative and I plug in 0, this goes away, but cosine of 0 is 1, so I get 1. Now the second derivative. These derivatives are going to start to get ugly. Okay, derivative of cosine of x is negative sine x. And then I have minus, in parentheses, a product rule right here. So the minus I'm not looking at. Derivative of x is 1 times sine x, plus derivative of sine x, which is cosine x, times x, so x cosine x. And cleaning this up, I get negative sine x minus sine x again, minus x cosine x, which is going to turn into negative 2 sine x minus x cosine x. That's the second derivative. And now if I plug in to the second derivative 0, this is 0, and that's 0. So I get 0. Great. All right. Wait a minute. Yeah, that's the second derivative. All right, so now the third derivative. The third derivative is, okay, derivative of negative 2 sine x is negative 2 cosine x minus the derivative of x cosine x. Wait a minute, that's the original function. What was the derivative of the original function? It was this. So I have minus, and so I don't have to do the work again. I just look at that first derivative, which is this. So minus cosine x minus x sine x. And cleaning up here, let me see what I get. Distribute the negative through, I get negative 3 cosine x. And then here to here, plus x sine x. If I plug in to this, 0 kills this off. Cosine 0 is 1, I get negative 3. All right, so let me write down over here so I have it. I have the 0th derivative at 0 is 0. The first derivative at 0 is 1. The second derivative at 0 is 0. The third derivative at 0 is negative 3. I'm hoping that when I do the fourth derivative, I get 0 again. Fifth derivative, maybe I'll get positive 5, right? 1, negative 3, positive 5, negative 7 when we do the seventh derivative. I need enough to pick up a pattern. So let me keep going here. I'm at the fourth derivative. Crap, I just erased some stuff I might need. The fourth derivative is the derivative of this. Well, the derivative of negative 3 cosine x is going to be positive 3 sine x, and then plus the derivative of x sine x, which I've done before. I'll do it right now. It's going to be sine x plus x cosine x. So I had to do product rule on this. And then when I put those together, I get 4 sine x and then plus x cosine x. Now if I take that fourth derivative and I plug 0 in, this is 0, that's 0, so I get 0. So it's exactly like I thought it was going to be. Fourth derivative at 0, 0. And I'll do the derivative maybe one more time. If I get a positive 5, I'm going to feel good about what's happening here. So the fifth derivative at x, the derivative of sine of x, cosine of x, but there's a 4, so 4 cosine x. And then plus, now product rule on this, we've done this already, it's cosine x minus x sine x. And then when we put these two together, I get 5 cosine x, then minus x sine x. And now if I take that fifth derivative, I plug 0 in, this goes away, I get cosine of 0 is 1 times 5, I get 5. I think, are you happy that what we're having is all the evens are 0, all the odds are just, 1, 1, 3, but this time negative 3, 5, 5, next one should be, 6, 0, and then 7, negative 7, then 8, 0, then 9, positive 9. So let me start writing out this Maclaurin series. So I know that I'm going to have this f of x, x cosine x, should be equal to, remember I'm getting my c sub n right now, so it's the zeroth derivative at 0, which is 0, over 0 factorial x to the 0, plus now the first derivative at 0, which is 1, over 1 factorial x to the first, plus now 0 over 2 factorial x squared, then plus, let's see, actually we know what's going to happen with the third, I'm going to get minus. So minus 3 over 3 factorial x to the third, and then plus 0 over 4 factorial x to the fourth, and then the 5 was a positive, so plus 5 over 5 factorial x to the fifth. I'll do 2 more. Plus it should be 0 over 6 factorial x to the sixth, and then the next one should be minus 7 over 7 factorial x to the seventh, plus dot dot dot. Now let me rewrite this with all the zeros gone. So this is gone, this is gone, this is gone, this is gone. So we have 1 over 1 factorial x to the first minus 3 over 3 factorial x to the third plus 5 over 5 factorial x to the fifth minus 7 over 7 factorial x to the seventh. What would the next one be? 9 over 9 factorial x to the ninth. Next one, minus 11 over 11 factorial x to the 11th plus. And now I need to come up with a formula for this. I'm going to start my index at 0 and go to infinity. So, well, this is odds again, right? I've got odd number. Let's look at this one. Odd, 1, 3, 5, 7, 9, 11. Oh, the alternating. Oops, I should take care of the alternating. I need to start with a positive, so negative 1 to the n will work. And then all the odds, starting with 1, so 2n plus 1 over all the odds again, factorial. And then all the odds again on the power of x, starting at 1. Okay, that's fine. That's good. Looks very similar to the last problem. Which one is this one? 8. Yeah, it's similar to the last problem. Now there's something we can do here, which is kind of nice. I don't know if you noticed this, but like all these factorials, like this is 3 times 2 times 1. This is 5 times 4 times 3 times 2 times 1. Like this 3 and that 3 would cancel, that 5 and that 5, and then this 7 and the first 7. So what you'd be left with here is 2 times 1. This one would be 4 times 3 times 2 times 1. This one would be, what, 6, because the 7s would cancel. 6 times 5 times 4 times 3 times 2 times 1. You can see it another way if you just look at your formula here. Negative 1 to the n times 2n plus 1 over, let's rewrite the bottom as 2n plus 1. Peel off 1. 2n factorial x to the 2n plus 1. So I'm just breaking this factorial down and noticing those two would cancel. So we get sum n equals 0 to infinity, negative 1 to the n, and then that cancels, so I have 1 over 2n factorial x to the 2n plus 1. Ratio test on this, if you did it, radius would be, that's an infinity. I think I can do 9 pretty quickly. Try and get 9 done. Sine hyperbolic, or hyperbolic sine. This one's going to be a lot easier than the one we just did because of the derivatives. The 0th derivative of this function is cosine hyperbolic x. If you plug in 0 into the hyperbolic, you have to remember what the hyperbolic meant. So, do you remember what cosine? Oh, why did I do that? Oops. I said it would be easy. Okay, the 0th derivative is actually nothing happens to it. And if you plug 0 into sine hyperbolic, you get 0. So go back and look at the definition of sine hyperbolic. We did that earlier this semester. It involved powers of e. So if you plug that 0 into it, you'll get 0. And then when you take the first derivative, the derivative of that is just cosine hyperbolic x. And if you plug 0 into that, you get 1. And the thing about sine hyperbolic and cosine hyperbolic is that the derivatives just keep on flipping back and forth from one another. They don't ever change signs. So the next derivative will be sine hyperbolic x, the next derivative cosine hyperbolic x, the next derivative sine hyperbolic x. And so what happens over here is you just get 0, 1, 0, 1, and you keep on going. Golly, Robert, 1. I'm hungry, it's late, I need to get home. And so what I'll do is just write out this Maclaurin series, and then I'll try and come up with a formula for it. So I know that this is equal to, all right, c sub 0, which was the 0th derivative at 0 over 0 factorial, which is going to be, we said that the 0th derivative was 0. So this is just going to be 0. So I'll write it down over here. 0 over 0 factorial x to the 0 plus, now this time we're going to get a 1 over 1 factorial x to the first plus this time a 0 over 2 factorial x squared. And it just, we keep on getting 1s and 0s. So 1 over 3 factorial x to the third plus 0 over 4 factorial x to the fourth, and then plus 1 over 5 factorial x to the fifth plus dot dot dot. Get rid of all the 0 terms. So you get 1 over 1 factorial x to the first plus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth plus 1 over 7 factorial x to the seventh, and you keep going. And now I'll come up with a sigma notation for this. Man, this odds is a big thing. Now notice all of these are always 1s. So I'm just going to have 1 over, now these are odd factorials starting with 1. So 2n plus 1 factorial, and then the powers on the x's are all odds starting with 1. So that should be it. That's your Maclaurin series for the hyperbolic sine function. Now, I think I'll skip 10, because 10 is just like this. It's cosine hyperbolic. So the only difference between this one and cosine hyperbolic is that you're going to have 1s here and 0s here. 1s and 0, 1, 0. So it's going to change, but I'll leave that to you to try and figure out. There's no magic in that. And that's it for this video. I'll pick up on number 11. I'm going to try and do 11 through 18. And then I'm also going to try and do 27 through, I don't know, 35 or so. All right, that's it. Working 8.7, picking up where I left off here at number 11. Now we're going to shift our attention now to Taylor series instead of Maclaurin series. Now the only difference between a Taylor series and Maclaurin series is that instead of centering our series at a equals 0, we're no longer going to do this. We're going to just center it at whatever they give us. So let's look at f of x is equal to x to the fourth minus 3x squared plus 1. And it's going to be centered at a equals 1. So this is a finite polynomial function, and they're giving you this example just as a warm-up, just to kind of get you to see how things are going to work. Assuming that this has a power series expansion, we know we can rewrite it as a sum n equals 0 to infinity c sub n x minus a to the n. In this particular case, a is going to be 1. So this should be able to be written like this. But we've got to figure out what our c sub n's are. So our c sub n's, the formula we have is it's the nth derivative at a over n factorial. Now in the past, the a has always been 0. And it's been pretty easy for us to plug in that number and get our c sub n. So let's just see, as we move through these problems, how using something other than 0 is going to affect how we actually come up with those c sub n's. So I will start off by trying to make a list of my derivatives. So first of all, the 0th derivative of this function is the function itself. And when I plug 1 into this, so notice I'm plugging in 1 instead of 0, I get, let's see, 1 minus 3 plus 1, right? So that's negative 1. And then I take the first derivative. So the first derivative of this function is 4x cubed minus 6x. And when I take that first derivative and I plug in 1, I get 4 minus 6, which is negative 2. And then when I plug in 2, the second derivative, I get 12x squared minus 6. And when I plug into the second derivative the value of 1, I get 6 out. And let's see what happens as I continue this. The third derivative is going to be 24x, and then that's it. So the third derivative at 1 is going to be 24. And you can see, because this is a polynomial function, as I take the derivatives, it keeps on getting nicer and nicer. Finally, the fourth derivative is just 24. And if I plug 1 into that, nothing happens. I get 24. And now the rest of the derivatives, every one of them from here on out is 0. And that means that this c sub n that we get, which is the nth derivative at 1 over n factorial, this is going to be equal to 0 over n factorial as long as n is, let's see, the fifth derivative and on, greater than or equal to 5. So that means I'm just going to have a bunch of zeros once I get to the fifth power in my power series. So it's time for me to write out my power series. I'm going to keep those right there. This function can be written as, I guess my voice is never going to clear up this semester. So I'm going c sub 0, right? C sub 0 is the 0th derivative at a, which is -1, over 0 factorial x to the 0, plus, now c sub 1 is going to be the first derivative at 1, which is -2, over 1 factorial x to the first, sorry, I messed up. It's not x to the 0, it's x minus a to the 0, plus then -2 over 1 factorial, then x minus 1 to the first power. See, it's not a Maclaurin series, so these powers here are going to have to be on the binomial x minus a, not just x. And then I have plus, let's see, I'm letting n be 2 now, so I'm in my second derivative at 1, which is 6. Over 2 factorial, and then x minus 1 to the second. Plus, now I'm at my third derivative, so 24 over 3 factorial, x minus 1 to the third. And then I have one more, because everything after this is 0. So 24 again over 4 factorial, x minus 1 to the fourth, plus, and then like I said, just zeros from here on out. So I don't really even need those. So I actually get a finite series. This is not an infinite series. It doesn't keep going forever, which kind of makes sense if you think about it. We're trying to approximate a polynomial function with a polynomial function. So, I mean, we're trying to approximate a polynomial function which is powers of x with the sum of powers of x. So it should be finite. All right, let's see what we get here. This is 1, right? Anything to 0 is 1. -1 over 0 factorial is 1, so we should just get -1 here. Plus, let's see, -2 over 1 factorial is -2, and then times x minus 1. So I'm just going to put -2 times x minus 1. And then over here, the bottom is just 2, and 6 divided by 2 is 3, so we get 3 x minus 1 squared. And then over here, remember 3 factorial is 3 times 2 times 1, so that's really a 6. And 6 goes into 24 8 times, so 8. Then x minus 1 cubed. And then plus, let's see, 4 factorial, 4 times 3 times 2 times 1. We said this was 6. 6 times 4 is 24, so that's just going to be 1. So that's just x minus 1 to the fourth. And that is our Taylor series. 6, and 3. Where's that one coming from? Oh, I see. It's my first problem. Cut me some slack here. This is not 8. That's 4. Okay, this was 6. 24 divided by 6 is 4. I did 24 divided by 3, which is 8, but it's 3 factorial. All right, well, got to get warmed up here, okay? Let's move on to number 12. All right, for 12, f of x is x minus x cubed. We're going to do this about a equals negative 2. A equals negative 2. So again, I'm going to need to start taking derivatives to come up with my c sub n's. So the 0th derivative of this function is just the function itself. Now what I need to do is look at the 0th derivative at negative 2. So when I plug in negative 2, I get negative 2 minus negative 2 cubed. That's, this right here is negative 8, but then I'm subtracting it, so positive 8. So this is a 6. And then I take the first derivative, which is 1 minus 3x squared. Then I look at the first derivative at negative 2. So I get 1 minus 3 times negative 2 squared. Negative 2 squared is 4, times 3 is 12. 1 minus 12 is negative 11. And this is going to do exactly what the previous one did. Eventually I'm going to get zeros here, which is going to be nice. But this is just negative 6x. And when I plug into the second derivative, negative 2, I get positive 12. And then my third derivative is going to be negative 6. And so when I take the third derivative and I plug in negative 2, doesn't matter, I still get negative 6. And then from here on out, when I take derivatives, these are all going to be zeros. So it won't matter. So here are the c sub n's, or a part of what I'm going to get my c sub n's from with these numbers, but then after a certain point, I'm not going to have them. So c sub n will equal the nth derivative at negative 2 over n factorial. That's going to be equal to 0 over n factorial, which is 0, as long as n is greater than or equal to, let's see, 4 here is where it starts. So I'm only going to have c sub 0, c sub 1, c sub 2, c sub 3, and that's it. I'm not going to have anything after that. So let's go ahead and write down the power series here. I'll leave these numbers here so I can refer to them in a minute. So this should be equal to this function. The Taylor series of this, about this, is going to be c sub 0, which will be this number, 6, over 0 factorial, x minus a to the 0. Now, this is going to be x plus 2, so I'm just going to change it now. And then plus, now it's going to be this one, which will be negative 11 over 1 factorial and x plus 2 to the first power. And then plus this number, which is 12, over 2 factorial, x plus 2 squared, and then one more, negative 6 over 3 factorial, and then x plus 2 to the third, and then it will be zeros the rest of the way. So I'm not going to worry about those. And now I'm going to clean this up. 6 over 1 is just 6, and then this right here to the 0 is 1, so I just get 6. And then negative 11 over 1 factorial is negative 11, x plus 2. And then let's see, 12 divided by 2 factorial is 2, so That's 6 x plus 2 squared. And then negative 6, remember 3 factorial is 6. So this is going to be negative 1 x plus 2 cubed. So that is the Taylor series for that function about a is negative 2. So, I mean, what is this thing? I mean, what does this represent? Let me do something here. I'm done, but let me show you something. Okay, so I'm putting distributing. Here I'm going to square this. X squared plus 4x plus 4. Still have to distribute negative 6 through minus. I'm going to expand this out. It should be x cubed plus 6x squared plus, let's see if I get this right, 12x plus 8. Pretty sure that's what it is. And then I get, let me try and clean up a little more. Distributing here this 6 through. Distributing the negative through. And let me collect like terms together, and I'll put it in, I guess it doesn't matter what order I put it in. Okay, how about numbers? How about numbers? 6 minus 22 plus 24 minus 8. So what is that? 6 take away 22 is negative 16. If I add 24 to that, I get 8, and then subtract 8, it's gone, so I don't have anything. These are gone. All the constants are basically gone. Now let's look at my x's. I have, where are my x's? Okay, I've got negative 11x and 24x. So that's going to be 13x. And then take away 12x, that just leaves me 1x. And then let's look at my x squared. 6x squared and negative 6x squared, they're gone. And then my x cubed, I have minus x cubed, that's all I have, minus x cubed. Oh, whoa, wait, hold on. That's the original function. Look at that. So what we've said is that if you want to approximate this function near negative 2, centered at negative 2, so imagine that graph around negative 2, what should I use to approximate it? I should use this, but it turns out that this is actually the same function. Does that make sense? If we're trying to estimate a finite polynomial with a power series, which is again it's a polynomial, then it makes sense that what we should estimate it with would be the polynomial itself. So this only happens when these are polynomials. If this is a polynomial, our best estimate of a polynomial is the polynomial itself. It's kind of amazing, though, that we can get that from all that work we did. Now, we would never really try and do a power series or a Taylor series or even a Maclaurin series for a polynomial. These first two examples were just to get us used to what we're doing and to kind of show you that, look, the result makes kind of sense. We're estimating a polynomial with a polynomial. 13, though, we have natural log x. And we are going to be looking at this centered at a is 2. All right. Now these derivatives are going to start to get kind of funky. So I think what I'll do is this. I'm going to move this over a little bit. F of x is natural log x, a is 2. So let's start looking at our derivatives. The 0th derivative is natural log x. If I take the 0th derivative and I plug in 2, I get natural log 2, which is just a number, whatever it is. Now, the first derivative is 1 over x, which is the same as x to the negative 1. Now I'm doing that because I'm going to take the derivative again in a second. It's easier to take derivative of this than this. So f prime, the first derivative at 2, you're going to plug 2 into this, you get 1/2. Now we take the second derivative. The second derivative, what happens here? The negative 1 comes out, so I get negative 1 x to the negative 2, which, remember, that's just negative 1 over x squared. So when I take the second derivative and I plug in 2, I have negative 1 over 2 squared. So I'm going to write that as 4. Now I take the derivative again. The third derivative, the negative 2 comes out and it becomes positive 2. And now x to the negative 3, which is 2 over x cubed, which when I plug 2 into that, I get 2 over 2 cubed, which is 8. Now I know I can reduce that, but because of a pattern we're trying to see here, I'm going to just leave it as is. Fourth derivative of this, the negative 3 comes out, I get negative 2 times 3x to the negative 4. Now, I agree that this is a negative 6, but again, I'm going to leave it out, negative 2 times 3 over x to the 4th, because I'm trying to get us to see a pattern here. If we plug into the fourth derivative the value of 2, we get negative 2 times 3 over 2 to the 4th power, which is 16. So let's try and figure out what's happening here. Well, let me do one more. Fifth derivative at x. So the negative 4 comes out here, it becomes a positive. I now have 2 times 3 times 4, x to the negative 5, which is going to be 2 times 3 times 4 over x to the 5th. And when I plug in 2, I get 2 times 3 times 4 over 32. All right, so let's work backwards. We have this right here is 4 factorial. This one up here is 3 factorial, but it's negative. This is 2 factorial, but it's positive. This is 1 factorial, but it's negative. And this is 0 factorial, but it's positive. Natural log 2 doesn't belong here. It looks like it's not part of a pattern. And that's okay, we'll deal with that in a minute. But everything else looks like it's following a pattern. Also, the denominators are just powers of 2, right? This is 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 squared, 2 to the 1st. So it looks like this number here, the derivative I'm at, right? This on the bottom is going to be 2 to that derivative. The top is going to be this number minus 1 factorial. So this would be like 5 minus 1 factorial. But then I also have the sign switching. You know, positive, this one before was negative. But it would follow the same pattern. We would have on the bottom 2 to the 4th, because this is a 4. And then this up here should be 4 minus 1 factorial. Now the negative, I'll deal with it, okay? I'll deal with that when I start to write this thing out. So what would the next one be? If we did the 6th derivative, we would get a negative 2 times 3 times 4 times 5 over x to the 6th. So when we plug in 2 into this, we get negative 2 times 3 times 4 times 5 over 64. So it's you can see it's following the pattern that I just mentioned. All right, so let's try now to write out, you know, our power series, our Taylor series for this, and remembering that we're going to be using this, and a was 2 over n factorial. All right, here we go. I will get rid of all this. So I'll need some room. I'll just keep this stuff on the side. Remembering that, this was the 0th derivative at 2, and then this is the first derivative at 2, second derivative at 2, third, fourth, fifth. So when I write this out, I have that this function, natural log of x, is equal to c sub 0, which is going to be this right here with 0 in there, which is that number over 0 factorial. So natural log 2 over 0 factorial, x minus 2, that's x minus a, to the 0. So that's the first term, plus c sub 1, which would be the first derivative at 2, which is 1/2, over 1 factorial, x minus 2 to the first. Then I have plus this one, negative 1/4, over 2 factorial, x minus 2 to the second. And then I'm going to get 2 over 8 over 3 factorial, x minus 2 to the third. So I'm right here, I've done those. The next one is plus negative 2 times 3 over 16 over 4 factorial, x minus 2 to the fourth. I'll do one more. Plus 2 times 3 times 4 over 32 over 5 factorial, x minus 2 to the fifth, plus dot, dot, dot. So that's my Taylor series for natural log of x about a is 2. Hey, come on in. And now I'm going to try and maybe clean this up and get a formula for this. So the first one here, this is 1, that's 1, so this is just natural log 2. We said that one didn't follow into the formula too much. And then what I'm going to do here is I'm going to clean up this fraction. This is like 2 fractions, so I can flip, so it becomes 1 over 2 times 1 factorial, x minus 2 to the first power. This one becomes minus, because there's a negative there, 1 over 4 times 2 factorial. So again, writing that like that and flipping it, x minus 2 squared, and then plus, and then we're going to go 2 over 8 times 3 factorial, so flipping again, x minus 2 cubed, and then minus, because this one's negative, 2 times 3 over 16 times 4 factorial, x minus 2 to the fourth, and finally, if I can fit this in here, plus 2 times 3 times 4 over 32 times 5 factorial, x minus 2 to the fifth, plus dot, dot, dot. All right, so remembering what we had earlier, we said that this one didn't follow the pattern, so I'm not going to worry about it. This number right here, this number right here, this number right here, this number right here, these were all powers of 2, right? And these were all factorials, right? But they were always going to be, there we go, those are, these factorials would be equal to the power up here, right? These factorials would be the power. And then in the numerator, this, 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 and this were factorials, but they were always 1 less than the power out here. So this is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. So with that in mind, let me try and rewrite everything again. This is natural log 2 plus 0 factorial over, this is 2 to the first power times 1 factorial times x minus 2 minus, this right here is 1 factorial over 2 squared times 2 factorial x minus 2 squared plus the top here is 2 factorial over 2 cubed times 3 factorial x minus 2 cubed minus, this is 3 factorial over 2 to the 4th times 4 factorial x minus 2 to the 4th, and finally plus 4 factorial over 2 to the 5th times 5 factorial x minus 2 to the 5th. I think I'm off camera here. It's good enough. All right, so now what I'll do is I'll try and write this in sigma notation. So this should be equal to, now this didn't fall into the pattern, so I'm just going to put natural log 2 here, plus sum n equals 0 to infinity. All right, so this first one, 0 factorial. If I'm starting at n is 0, then it's going to be n factorial on top. All right, 2 to the first power. So if I'm starting at n equals 0, that needs to be 2 to the n plus 1. So when I plug in 0, I get 1 here. When I plug in 1, I'll get 2. When I plug in 2, I'll get 3. When I plug in 3, I'll get 4, and so on and so forth. Same with the factorials. This is a 1 factorial. So this is going to be n plus 1 factorial here. So when I plug in 0, I get 1 factorial here, 0 factorial here, 2 to the first power here. So that takes care of this. And then the x minus 2, the power on this needs to start at 1 and go 2, 3, 4. So I'm going to do n plus 1 there also. And that should be our Taylor series. But there's a little bit of cleaning up I can do. I can rewrite the n plus 1 factorial as n plus 1, peel off the n factorial, cancel. So we should get natural log 2 plus sum n equals 0 to infinity. I'm going to run out of room. I'll do it right here. So this is equal to natural log 2 plus sum n equals 0 to infinity. On top you have a 1. On the bottom you have 2 to the n plus 1. And then n plus 1 here. And then times x minus 2 to the n plus 1. And that is your Taylor series for natural log of x about 2. Check it real quick. Yeah, that's fine. The book answer, they switched the index here to 1. So I'll do that just to show you. This is correct. It's not wrong. It's just they want to have a different index. That's fine. So what I'm going to do is change this index to a 1. So I have to replace all my n's with n minus 1 in order to do that. So when I put n minus 1 here and add 1 to both sides, I'll get my sum to start at 1. And then 1 over, if I replace this with n minus 1 plus 1 is just 2 to the n minus 1 plus 1 is just n. And then x minus 2, same thing here, n. So I believe that's what the book shows as the answer. I forgot the alternating part. Shit. Forgot the alternating part. It had to alternate starting with a positive, right? And then go negative, positive, negative. So I'll adjust that. To do that, start at positive, I do that, right? Here, I do that. So if I plug in 0, I get a positive 1. If I plug in 1, I get negative. So that'll give me my alternating. But then when I replace that with n minus 1, it'll be that. I had a feeling I was going to forget that alternating part. Okay, that's it for that one. Yeah, just remember, it was an alternating series. So I had taken care of all this stuff and I was focusing all of my attention on that. I forgot that we alternated, so I need to start at positive, then negative, positive, negative. So this will take care of that. That'll make that happen. I don't feel like going back and redoing that whole problem, so I think hopefully you understand. You know, what's going on? I felt good today. I thought I was going to come in here and have a great session. I guess I'm just getting ready for the break. Next one, 1 over x is the function. And we're going to do it about a is equal to -3. All right, so here we go. We are going to start doing our derivatives. The 0th derivative. Remember, this is x to the -1. So the 0th derivative is just 1 over x. X to the -1. So when we plug in -3, let me just make sure it's -3. It is. We get, in here we get -1/3. Now we take the first derivative and we get negative x to the -2, which is -1 over x squared. So then when we plug into this derivative -3, we get -3. When we square it, it's going to be +9, so it's not going to matter. We get -1/9. And then when we take the second derivative, this is the -2 comes out, hits this, becomes +2. So we get 2x to the -3, which is going to be 2 over x cubed. So when we plug in -3, we get 2 over 3, -3 cubed is -27. So far they're all negative. Let's see, when we do the third derivative, we get -6. Or actually, I'm going to do what we did before, because I know where that's headed. -2 times 3, x to the -4. That's -2 times 3 over x to the 4th. When I plug -3 in there, on the top I have -2 times 3. On the bottom I have -3 to the 4th power. So that's -3 times -3 times, it's going to be positive, and it's going to be 81. But we're already noticing that all the denominators are always just powers of -3. So again, I have a negative number. Let's do one more. So when the -4 comes out, I get a positive, so 2 times 3 times 4, x to the -5. So this is 2 times 3 times 4 over x to the 5th. Because it's the 5th power, when I plug -3 in, I'm going to get a negative, because this is the 5th power. So even though the numerator is positive, the denominator is going to be negative. And then I'm just going to put here -3 to the 5th. All right, so what's the pattern? what's the pattern? They're all negative, right? They're all negative, so that's good. I don't have to worry about that. They're all negative. The tops looks like they're factorials. That looks like 4 factorial, and that's 4. This looks like 3 factorial, and that's a 3. That looks like 2 factorial, that's a 2. That looks like 1 factorial, that's a 1. That looks like 0 factorial. So again, forget the negative there. And then the bottoms are all just powers of 3. 3 to the first, 3 squared, 3 cubed, 3 to the fourth, 3 to the fifth. And so this number 5 is always 1 more than this, right? 5, 4, 4, 3, 3, 2, 2, 1, 1, 0. So I think I can come up with a general formula for my C sub n. I think a general formula would be pretty easy to come up with here. But I'm going to put it all together and try and write the power series out. So let me write these down over here. I have negative 1 over 3. I have negative 1 over 3 squared. I have negative 2 over 3 cubed. Negative 2 times 3 over 3 to the fourth. And negative 2 times 3 times 4 over 3 to the fifth. So those are my derivatives evaluated at negative 3. 0th derivative first, derivative second, third, fourth. I'm just writing those down so I can look at them in a second here. So my Taylor series for this, 1 over x, should be equal to the 0th derivative at negative 3, which was negative 1/3, over 0 factorial, and then x minus negative 3, which is plus 3 to the 0, plus, now again, negative 1 over 3 squared over 1 factorial, and then x plus 3 to the first, and then plus negative 2 over 3 cubed over 2 factorial, x plus 3 squared, and then, let's see, negative 2 times 3 over 3 to the fourth over 3 factorial, x plus 3 to the third. I have enough room, I can do another one, plus negative 2 times 3 times 4 over 3 to the fifth over 4 factorial, x plus 3 to the fourth. So I'm wondering if I should flip again to make it easier for you to see. This is negative 1 over 3 times 0 factorial, x plus 3 to the 0. And then this is going to be another minus. So minus 1 over 3 squared times 1 factorial, x plus 3 to the first power, minus 2 over 3 cubed times 2 factorial, x plus 3 squared, minus 2 times 3 over 3 to the fourth times 3 factorial, x plus 3 cubed, minus 2 times 3 times 4 over 3 to the fifth times 4 factorial, x plus 3 to the fourth, plus dot, 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 plus dot, dot, dot. So I'm ready to write my sigma notation, but I want us to notice something that we could do right now. We said these numerators were factorials, right? This was 4 factorial, 3 factorial, 2 factorial, 1 factorial, 0 factorial. So let's rewrite those. 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and that would continue. And do you see that they cancel with the denominator? So all we really have is this. we have a negative on every one of these. So we have a negative, sum, n equals 0 to infinity. And then this is 3 to the first power, right? And then the only other thing we have is x plus 3 to the 0 power. So I need to put 1 over 3 to the n plus 1. That'll give me 3 to the first power. And then x plus 3 to the n. So if I plug in n is 0, I get 3 to the first, and then I get x plus 3 to the 0. So that'll give me this. If n is 1, I get this, and then this. And that continues. In the negative, I could have the negative here, or I could put the negative just up in here like that. And that should do it. Let me see. Yeah, go figure. They put the negative on the outside. All right. Okay. You do? Okay. This is, let me see how much I've got into this. I'm 40, no, I've got 45 minutes onto this video.
It was pretty intense.
Which one are you working on?
8.6.
8.6? Okay, this is 8.7. So let me do one more, okay? And that'll be about an hour of video. That'll be perfect for me to upload. So let me just do one more of these, and then I'll help you out. 15. I'm pretty sure I'm doing 15 in class. F of x equals e to the 2x. We're going to do that about a is 3. All right, let's start doing derivatives. So the 0th derivative of this function is itself. And if I plug in to this 3, I get e to the 2 times 3, which is e to the 6. If I do the first derivative, because of chain rule, the derivative of this is itself, but then a 2 pops out, so I'm going to get 2e to the 2x. If I plug in 3 into that first derivative, I get 2e to the 6th. If I do the second derivative, same thing, another 2 pops out, so now I get a 2 squared, e to the 2x. And the second derivative with 3 plugged in will just be 2 squared times e to the 6th. And then the next time, the third derivative, this one's actually going to work out pretty clean. I'm going to get 2 cubed because another 2 pops out. And then when I do the third derivative at 3, I get 2 to the third e to the 6th. And then I keep doing this. So it looks like my c sub n's are going to be, let's see, on the first one, well, here this is 2 to the first, this is 2 to the second, 2 cubed, but this one right here I could write as 2 to the 0, e to the 6th, right? So it looks like my c sub n is going to be 2 to the n, e to the 6th. That never changes in all of them, over n factorial. But I don't even think I need to write all these out. I've got a nice clean formula for it, right? If c sub 0, 2 to the 0 is 1, e to the 6 over 0 factorial, that's this. Well, this part is this. And then this one, if c is 1, we get this, that's that. So I think we're in business. I think I can just go straight to the series without writing it all out. It should be that e to the 2x is equal to the sum n equals 0 to infinity of the formula for c sub n, which is 2 to the n e to the 6th over n factorial, but then x minus a to the n. that'll do it. I'll do one more. We'll do 16. F of x, sine x, a is pi over 2. So some derivatives. Zeroth derivative is itself. Plug into the zeroth derivative, pi over 2. Sine of pi over 2 is 1. Okay, first derivative, cosine x. Plug in pi over 2 into cosine x, and you get 0. Second derivative, negative sine x. Second derivative, pi over 2. So if you do sine of pi over 2, it's going to be 1, but then make it negative, so negative 1. And then third derivative, derivative of that is negative cosine x. When we plug in pi over 2, cosine pi over 2 is 0. Fourth derivative, sine x. We're back to where we were earlier. Fourth derivative, pi over 2 is 1. So what's going to happen now, because we're back to sine, is that we had 1, 0, negative 1, 0. So we're going to have 1, 0, negative 1, 0, 1, 0, negative 1, 0, and that's going to continue. So I think for this one, because I don't have a nice clean formula that I can write for the c sub n, what I'm going to do is I'm going to write out these values. Just going to remember 1, 0, negative 1, 0, and then it repeats 1, 0, negative 1, 0. I'm just going to write it out for sine of x. So here we go. First, we have sine x equals, all right, this number, 1, over 0 factorial, x minus pi over 2, x minus a to the 0, plus, now this number, 0, over 1 factorial, x minus pi over 2 to the first, plus, negative 1 over 2 factorial, x minus pi over 2 squared, plus 0 over 3 factorial, x minus pi over 2 cubed, plus 1 over 4 factorial, x minus pi over 2 to the fourth, plus 0 over 5 factorial, x minus pi over 2 to the fifth. Do I need to go more further? All of my odd ones are not here. And all of my even ones are there, but they're also alternating in sign. So, yeah, let me just put the next one. Next one that would be out here would have been a negative 1, and then it would have been 6 factorial, x minus pi over 2 to the sixth. So that gives me my pattern. Look, 1, 0, negative 1, 0, 1, 0, negative 1, 0, and then it would continue. So this is sine x equals, all right, this is a 1, that's a 1, so I get 1. Okay, this is minus 1 over 2 factorial, x minus pi over 2 squared. The next one I get is plus 1 over 4 factorial, x minus pi over 2 to the fourth. The next one I get is minus 1 over 6 factorial, x minus pi over 2 to the sixth. Any guesses to what the next one would be? Well, it's going to be plus, and it's going to be even. So 1 over 8 factorial, x minus pi over 2 to the 8th. And then the next one would be minus 1 over 10 factorial, x minus pi over 2 to the 10th, and then so on. So let me make sure I don't mess this one up. It's alternating, so I'm going to start my sum, n equals 0 to infinity. I need to alternate, I need to start, I believe I can get this still within my formula. So to start positive, negative, so I'm going to use -1 to the n. Now, all of these fractions out front are just 1 over factorial. So 1 over 2 factorial, 1 over 4 factorial, 1 over 6 factorial, 1 over 8 factorial, 1 over 10 factorial. That's 1 over an even factorial. In fact, this first one right here, this is 1 over 0 factorial. So what I'm going to do here is I'm going to put 1 over. Now I need to create just even numbers, but I need to start at 0. So how about 2n factorial? So now if I plug in 0, I get 0. When I plug in 1, I get 2. When I plug in 2, I get 4, 3, 6, 4, 8, so on and so forth. So that should take care of that blue part. And then out here, it's the x minus pi over 2. And then those are all also just even powers. So, and I want to start actually at this first one, this right here. So I want to start at 0. So same thing, 2n up here. And that should create the series. So that is your Taylor series expansion of sine x about the value pi over 2. Let me check it. 2 factorial -1 to the n, yes. All right, that's it.